Yes.
Lightning talk. So
It is a lightning talk.
welcome Joshua for the talk. Please continue.
All right. Well, first of all, welcome to perhaps the most provocatively titled lightning talk of this JuliaCon. I hope to maybe be a cherry on top of that wonderful talk we just saw. My name is Joshua Ballanco, and today I'd like to talk to you a little bit about killer apps. Okay. So I presume this is probably a term that many of you have heard before, but just to review real quickly, I think Wikipedia's page on killer apps actually summarizes it quite succinctly. A killer application is any computer program that is so necessary or desirable that it proves the core value of some larger technology. So that is to say, it's not necessarily the best application for a system or the only application for a system, but it's the application that sort of opens people's eyes to see that the thing that they haven't really been paying attention to before is worth a look. And so I'm very excited about the great success that Julia has had in a number of fields, but throughout the JuliaCons and all of the discourse and Slack discussions, I've always felt like there is still something that when somebody new came to the community and said, yes, but why Julia? That we didn't quite have that one thing that we could point to. So I got to thinking about what would that look like. Well, it should prove the value of Julia's core technologies, and as we just saw, those are multiple dispatch and its type system. And more importantly, it doesn't have to be a new concept. Right? So the Julia community is on the cutting edge of a number of different fields. So I feel like there's sometimes a temptation to sort of push forward, but a lot of people who are coming into a language community new aren't necessarily interested in the cutting edge. They just want to know, how can I do the things that I've been doing, but better? And that's really the key, is that we have to show people how Julia makes something that they do so easy that they forget they ever did it some other way. Okay, so since this is a lightning talk, and I'm not sure I'm going to get through all the rest of these, I wanted to make sure that I gave you the takeaways that I want you to bring from this talk up front. And so that is, as we just saw, multiple dispatch really is mind-bendingly powerful. It is a very important technology, and it's something that the more you think about, the more you realize just how powerful it is. Also, if you've been trained in the traditional object-oriented programming education system, there's a temptation to automatically associate types with things, right? We've all seen the, a car is an object type demonstration, and I feel like that's a little bit restrictive in our thinking, because types can describe concepts, not just things. And so if we keep these two things in mind, and we start to experiment with what we can do with types as concepts and multiple dispatch, I think you can come up with some very interesting, very creative applications of Julia. And when I did this, the one I landed on was state machines. Now, unfortunately, I don't have time to go into a whole explanation of state machines. Hopefully, it's a concept many of you are familiar with. But in short, a state machine is essentially a collection of states and transitions between those states. Well, if we allow ourselves to think of types as concepts, then states and transitions can both be types. And if we remember that multiple dispatch allows us to dispatch on all the types of the arguments given, we can actually use it to simplify the implementation of a state machine. So what does that look like? Well, let's bake a cake. Okay, so we're going to describe the process of baking a cake as a state machine. We're going to start off with some abstract types for state and transition, and you'll see why those are important a little later. Just customize an error to throw when we've reached an invalid state, and we have an enum to describe the ingredients we need. So the initial state we're going to begin in is the state of needing ingredients. And we're going to keep track of the ingredients that we've already gathered in this state. And the way we transition from this state is by gathering ingredients. After we've gathered all of our ingredients, the next state we'll be in is the state of mixing the batter. We have a list of ingredients now that we have to add in a particular order, so we keep track of the ones that are remaining, and we've got a little convenience constructor there to define the order that we should add them in. Dry ingredients first, right? And the transition out of mixing the batter is to add ingredients, right? We add ingredients, and eventually we end up with a raw batter if we've done it in the right way, or a ruined batter if we didn't. Transitioning out of a raw batter involves baking, and depending on how well we've done, we either end up with a tasty cake or a burnt cake. Okay, so these are our states and transitions described as types. So how do we implement the state machine? Well, this is a trick that I've used a number of times in Julia that I really like, and that is basically we can define for ourselves a base case and take advantage of Julia's multiple dispatch and the fact that it always dispatches to the most specific function for a method to basically say that by default, any transition from any state is an invalid state. And now we're going to define the valid states and the valid transitions. So first off, starting from needing ingredients, we gather ingredients by pushing them onto the set of ingredients we've already gathered. And we check to see if we've gathered all of our ingredients. If we have, we're going to proceed to mix batter. Otherwise, we remain in this state. Transitioning out of mixing batter involves adding ingredients. We check to see that we've added the next ingredient in the list. And if not, we've ruined the batter. But if we have, then we check to see if there are any remaining ingredients that we need to add. If not, then we have our raw batter. If there are still more ingredients to add, we just remain in that state. And then finally, the process of baking simply checks the temperature we're baking at. If we've baked it too hot, we've burnt the cake. If not, then we have a nice tasty cake. Okay, so just to sort of demonstrate how this works on a piecemeal fashion. So if we started off needing ingredients, we gather some eggs. You see we transition back to the needing ingredients state, but this time we have some eggs in our state. If we try and add water to the batter when we haven't even gathered any ingredients, then obviously that's an invalid state. Now, what's really interesting about this approach, I don't know if you've seen it, but we can now describe an entire recipe as a series of transitions and simply reduce the step function across the recipe, starting with the needing ingredients state, and we end up with a tasty cake. Okay. All right, so that's a fun little trick, and I'm going to run out of time here. So we don't have time to do all of regular expressions. If you're familiar, though, you might know that regular expressions can be described as state machines. We're just going to do a simple string matcher. So here I'm abusing the type system a little. Characters can be parameterizations of a type. We can describe some wildcard types and or matchers. Right? And these matchers are states, basically. And the transitions are going to be value types for the characters that we encounter. So defining matching a character is very simple with the type system. Either both parameterizations are the same, in which case we proceed to the next state. Otherwise, it's not a match. Wildcards match anything. And or is quite simply check the one, check the other. If one of them matches, proceed to the next. Otherwise, we return nothing. Finally, just to ensure that we maintain consistency, we always return matched if we've already reached a match and nothing if we've already reached nothing. And then implementing regular expression matching is as simple as mapping a value across the characters and reducing, again, step across the characters, starting with the regular expression as our initial state. All right, and yeah, so that's a demonstration of matching against a regular expression that would match Julia. So. All right, anyway, last thing I just wanted to point out is that there are many other state machines that we can implement, and perhaps one of the most provocative that I'd like to explore further is all of the HTTP protocol can be implemented as a state machine, and I think it would be really interesting to try that in Julia. So, thank you. Yeah, I've looked at a number. Actually, there used to be a statemachine.jl package. I think it's no longer maintained. But the thing is I feel like a lot of the packages around parsing and state machines, I used to follow the one parser JL, PegJL, I think it was. I feel like they start with the assumption that you have to facilitate describing parsers or state machines in some other fashion. The sort of epiphany that I had when I was thinking about the subject of this talk was that the Julia language itself is already expressive enough We don't have to accept, BNF notation. We don't have to accept, Lex, Yak, whatever. We can just do it in Julia. Now, that's an interesting question because one of the reasons that I wasn't able to show regular expressions is that it's difficult to do them in a state machine that's a directed acyclic graph. Usually you end up with cycles in the state. And that's hard to do without enabling, making the states modifiable. But yeah, if you had modifiable states. The other thing that I didn't get time to show is you can also modify your state machine by injecting new methods, right? So you no longer have to rewrite your entire state machine when you want to insert a state. You can just simply rewrite that particular implementation of the step function.
Okay, thank you very much.